everybody. Welcome to our next session at our JAX London online event. I'm Hartmut, I'm editor at Software and Support Media, and we are organizing JAX London here. And of course, we are happy to have this conference here in this remote manner. And we are seeing now Simon Ritter is waiting for his talk. Hi, Simon.
Hello.
Everything's okay? You're sitting obviously in a home office setting.
Yes.
As many of us these days. But yeah, that's it. Next year, probably locally in London again. But we can have great talks here also in home office fashion. Yeah, I think Simon Ritter is really known to everyone here, working with Java since its beginning, that Sun Microsystem. Now you are at Azul Systems. Yeah, the talk is about what you are doing here with JVMs at Azul, I guess. Yeah?
That's right, yes.
Okay, then as usual, feel free to ask your questions out there. You have the chat, you have the questions tab, and yeah, let's make that interactive. And with this, I hand over to you, Simon.
Okay, thank you very much. I shall just share my screen and my slideshow. Now, hopefully everybody can see my screen. And we shall begin. Yes, so my name is Simon Ritter. I am the Deputy CTO of Azul Systems. And the idea behind this presentation today is talk about how we think that we build a better JVM. And the whole idea behind that is to look at ways that we can alter the performance characteristics in terms of things like latency and in terms of throughput. And in order to do that, what we need to do is to start by having a think about what we really mean by performance. And so I've described this as speed in the Java world, because Java is a bit different, simply because we have this Java virtual machine that presents a layer between our application and the operating system. Normally, if you're running things like C or C++, then you compile it into native instructions and you run it directly on the operating system. But with Java, write once, run anywhere, we have bytecodes, and then we have the JVM that handles a lot of things for us. Now, what I did was I thought about this and I said, okay, so how do we perceive the idea of perfect performance in terms of the JVM? So not applications, but the JVM itself. And I came up with a pretty detailed graph of what I would expect for the perfect performance of the JVM. As you can see, it's not a very exciting graph. It just shows that what we would really like is for our JVM to start up and to provide us 100% of possible performance at the beginning, right from the start, and then simply give us 100% of possible performance all the way through the application until we stop. So not a very exciting graph, not very interesting. But the thing that actually we need to look at is how that graph presents itself in reality if we look at a typical kind of application. What we tend to see is something which is a lot more like this. So the profile of that graph is very different to the ideal. We see that we start off very slowly, then we gradually warm up, we get to our optimum level of performance, but we've still got these dips in performance all the way through. Now, if we look at this graph in a little bit more detail and understand what's actually going on, then we can talk about how we can actually address that and improve the performance of the JVM for our applications. So the first thing is to understand that because we're using bytecodes, bytecodes are instructions of a virtual machine, Java virtual machine. And what happens is that when the JVM starts up and it loads class files, it has to take those bytecodes and convert them into the necessary instructions for whichever platform it's running on, whether it's Windows, whether it's Linux, Intel, ARM, whatever. And that's what's called interpreting. So we take the bytecodes, and every time we see a bytecode, we convert it, we interpret it into those native instructions. Now, often that's a fairly simple process because it's a one-to-one mapping if it's a very simple operation. But for more complex things, it's a lot more involved and requires a lot more work. The thing is that with interpreting, we don't do any form of optimization. So we're literally taking bytecodes, interpreting them, and doing the same thing every single time. That has a big impact on performance. This is why when Java was first released, people said it was slow compared to C and C++. Now, the developers of Java looked around and they said, well, how can we improve that? And so they said, okay, let's use what's called just-in-time compilation. And so we see that as the system starts to improve, what's happening is that the JVM is looking at how many methods are called and how often those methods are called. So it keeps track of how many times you call a particular method. When that method reaches a certain threshold in terms of the count, let's say 10,000, then the JVM will say, aha, this is a piece of hot code. It's a hotspot in our code, hence the name of the JVM. What it then does is it says to itself, it says, okay, let's compile this into native instructions and keep those so that we don't have to keep doing the interpreting. We can have the compiled code and we can use it every time we need to call that method. At that point, it uses a JIT compiler called C1. It used to be called the client compiler. And the idea of C1 is to compile that code as quickly as possible, but it doesn't provide a lot of optimizations. So it compiles quickly, but doesn't heavily optimize. Having done that, the JVM, every time we call that method, will use that compiled code. It will also collect profiling information about how that method is being used and what happens within that method. When we reach a second threshold, where that particular method is called a lot of times, then the JVM will decide at that point that in order to get better performance, it will then recompile that code and use a different JIT compiler. And in that case, it's using a thing called C2, or what used to be called the server compiler. Now, that compiler takes longer to compile code, but it can apply a lot more optimizations to get better performing code. It uses the profiling information that was collected during the C1 compiled code being run, uses that to then perform these optimizations and then allow us to run our code faster. So what we'll see is that gradually more and more methods get compiled with C1 and then C2 until we reach a steady state of code where all the hotspots are being compiled both with C1 and C2. But you'll also see there are some big dips in performance as we go through that, and that's down to what are called deoptimisations. One of the things that JIT compiler can do very effectively is use what are called speculative optimizations. And speculative optimizations take the approach that if we look at the way that our application has run up to this point, let's assume that it will continue to run in that way and optimize based on that. Simplest example is if we have an if statement in our code, and up until now, we've only ever gone through the true branch of the if statement. So we'll optimize based on the idea that we continue to only go through the true branch. And that may be true, but we may also hit a point where something changes and we need to go through the false branch, at which point the code that we've optimized becomes invalid. So we have to de-optimize by throwing that code away and then recompiling it with a new set of assumptions. So those are de-optimizations. So we reach our steady optimized state, but we still see these dips in performance. And those are due to a different aspect of the way that the JVM works. That's down to garbage collection. I'm sure that anybody who's written any real Java code and deployed it in production will know about garbage collection pauses. So what we're faced with is two specific challenges because we're using a managed runtime environment. This is really good for us as developers because the JVM takes care of a lot of the work for us, but it does have an impact on the way that the JVM performs. First of those is, as we already know, the garbage collector. And the problem with the garbage collector from a performance perspective is it's inherently non-deterministic. We can't predict when it will run, and we can't predict how long it will run for, because we don't know what our application profile is going to be and how quickly we'll allocate objects and so on. One of the problems that we see a lot with garbage collection is that the pause times can be very large. You know, they can be hundreds of milliseconds, they can be seconds, minutes. Largest pause I've ever come across was 1.5 days. That's a very extreme case, and hopefully you never see that. But we do need to look at how we could improve that in terms of latency and response time for our applications. Second thing is, as we've already explained, is that we're dealing with bytecodes, not machine code. And how we approach that compilation using JIT compilation, more than one JIT compiler, and speculative optimizations, all of those things, that affects how long it takes the code to warm up to get to that optimum level of performance. So that's the way that your standard hotspot JVM works. What if there was a better way of doing this? And so That's what we at Azul have come up with, is what we call Zing. And Zing is an alternative JVM which uses some different implementations for certain things, not everything, but some different things to change the performance profile of the virtual machine. If we look at some of the basics of Zing, what we did was we said, okay, we want to improve things, but let's not start from scratch. Let's not go all the way back and write a completely new JVM. We don't need to do that. Much of the code works very well, but there are certain bits that we do need to change. So we started with the OpenJDK source code. It's the open source version of Java, good starting point, all the code's there. Very importantly, once we've made all the changes that we are going to talk about over the next few slides, we build our JVM, and then we run all of the standard TCK tests. It's about 150,000 tests that are used to verify that whatever JVM and JDK you produce matches the standard as defined through the JCP. And so each version of Java has a JSR, Java specification request. There is a specification associated with that that defines exactly what the JVM must do from a functional perspective. And so we need to run all those tests to make sure that we match that, and your bytecodes will execute in the same way functionally as they do on any other JVM. Clearly the performance will be different, but from a functional, how they actually execute, that's going to be exactly the same. Important thing about that is it means that it's a drop-in replacement for other JDKs and other JVMs. There's no requirement on you as a developer to change your code. There's no requirement on you to even recompile your code. You can simply take your existing class files, jar files, and run them with the Zing JVM rather than other JVMs. What we've done in terms of replacements is garbage collection. So we took all the hotspot collectors, serial, parallel, CMS, G1, and so on, took them all out and replaced them with one, which we call C4. And I'm going to explain what we do with that in a moment. The other thing that we've done is to look at how to improve memory management further. So we have these things called Zing system tools, and that works at the operating system level. So from a support perspective, we only provide Zing running on Linux. Technically, there's no reason we couldn't do it on Windows, but for simplicity and maintenance and so on, we only support it on Linux. Second thing we've done is more recently to replace the C2 JIT compiler with one that we call Falcon. And again, I'll explain what we've done there a little bit later on. And then the last thing is a sort of complementary technology called ReadyNow, which is designed to eliminate as much as possible this warm-up phase that we see in terms of the slow startup, gradually getting to our optimum level of performance. A little bit more detail about Zing system tools. As I said, this is designed to enable us to have better memory management. And what we did was we looked at the way that the Linux virtual memory system works, and that's a very good virtual memory system, but it's designed for general purpose applications. The JVM is a very specific application, and the way that it works with memory is very specific. What we did is we said, okay, let's put a sort of kernel module alongside the virtual memory system, enabling us to handle that mapping between physical and virtual pages in a better way for the JVM. Certain things we can do, like we know the cache status, we can then provide hot pages every time you want a new thread local allocation block. We can do some other interesting tricks in terms of contingency memory. So if your JVM gets to the point where it might throw an out of memory error, we can actually let it allocate more memory than you've allocated in your heap space, with the idea that you don't get a crash, but then we try and run the garbage collector more frequently to bring it back under the level that you want. One of the things that we found with that was that some people said, well, that's really good, but if we're doing things like microservices and we want to deploy into containers, having to install things on the host operating system isn't really very good. So in more recent versions of Zing, you don't have to install the Zing system tools if you don't want to, for heaps that are less than 1 terabyte. If you're going over 1 terabyte, you still need to, but I'm assuming that things like microservices, you're probably not going to need 1 terabyte or more in your microservice. Although I have come across people who do have microservices with 1 terabyte of heap space. Okay, let's talk about the actual technical details of what we're doing. So first thing is C4, and this stands for the Continuous Concurrent Compacting Collector. Essentially, that tells you exactly what we do. We run continuously in the background. We are fully concurrent. Unlike other garbage collectors where they do some parts of the garbage collection concurrently and some parts not, everything we do is concurrent with application threads. More importantly, we can do fully concurrent garbage collection and we can do compaction, meaning we can relocate objects within the heap at the same time that your application is running and do it completely safely. So that's the real key thing here, is that it's completely concurrent and it compacts the heap to eliminate fragmentation and make better use of the memory. From a basic idea, C4 uses similar ideas to other garbage collectors. So it is a generational garbage collector. Pretty much every garbage collector you find, with a couple of exceptions, use a generational heap. They divide it into young and old. Really, the reason for this is that if you look at the way that most allocations work in typical Java applications, almost all the objects that you're going to allocate will only be used for a very short space of time. And by allocating objects initially in this young space, you can do better garbage collection and remove a lot of the objects which have only been used for a very short space of time before they get promoted to the old generation, and that reduces the load on the old generation in terms of garbage collection. So we do the same thing, a little bit different in that we use the same algorithm for both the young and the old generation. Certainly if you look at Hotspot, they use different algorithms, we use the same one, and it really is about minimizing the pause times associated with garbage collection that actually happens. As I said, it is fully concurrent, it does compact, and all phases of our collection algorithm are parallel, meaning we can have multiple threads working on the data at the same time. Very important is that in our algorithm, there is no stop the world full compacting fallback situation. If you look at things like CMS and G1, then at some point they will give up and they will say there's too much fragmentation, we don't have enough free space, we need to do a full compacting collection on the old generation, and that takes a lot of time. And the time it takes is proportional to the size of the heap, not to the amount of data there. Bigger your heap, the longer your pause is. In terms of the algorithm we use, it is a three-phase approach: mark, relocate, and remap. How does this work? Well, the first thing we need to understand about is what we call the loaded value barrier. And this is how we're able to do fully concurrent garbage collection. The loaded value barrier is in effect a read barrier. Every time you access an object in your application code that you want from the heap, we will intercept that in order to determine certain things about what is happening with garbage collection and the state of that object relative to garbage collection. By doing that, we can enforce two rules on the references that we give to the application. First of those is that if we're in the marking phase, then every object that you get a reference to will be marked as live data. And that's very important because it means there's no accidental garbage collection of something that you think you're using, but we haven't marked yet, and it gets caught up in garbage collection and suddenly it disappears without you noticing. So that's one very important thing, is that we do mark every object that you get to make sure it's live data. Second thing is, if we're in the relocation or remapping phases, then you will always get the correct location of that object. Even though we're moving it around in the heap, we will give you the correct location of that object so you can make changes to it and it doesn't get lost because we've copied the object to a different place and suddenly we haven't updated the header, and so you lose the changes that you've made. That won't happen. So we guarantee that you get the right place to make changes and those changes don't get lost. As I said, this allows us to do full concurrent marking and relocation. Now, a lot of people then say, well, hang on, surely that's going to degrade performance because you're intercepting every reference to an object, and we do that a lot. Well, yes and no. The reality is that because we use bits in the object header, we're able to do that in a very light touch way. So literally it's two instructions, test and jump. We test some bits in the object header. If we need to go and do some work, we will jump to a handler, but most of the time we simply don't have to do anything. So we go on to return the reference to you as the application, and it doesn't provide any degradation in performance that way. So literally two instructions. If you look at that in terms of the the underlying architecture, the chip architecture. On an Intel processor, that's 1 micro operation, which is less than 1 nanosecond. So it really isn't a big impact in terms of performance. Certainly, if you look at the time it takes to do L2 cache accesses, L3 cache, main memory, way more than any of the effect that you will see from the loaded value barrier. How does this work? Well, what we do when we're doing our marking phase is to start with the same approach that a lot of other algorithms use. We create a root set. And the root set is simply a list of all the objects that you have directly accessible from your application code. We scan the stack, we look at all the registers, we look at all the static variables, and we build up a list of objects that you can directly access. Obviously, many of those objects will reference other objects. So we need to trace through the references from every object to every other object that's still accessible and mark those. So we take the root set and we start working through that. Garbage collection threads will look at the first element on the root set the bit in the header to say this is still a live object, and then start tracing references to other objects and marking those to say they're still in use. Because the root set consists of a set of independent data, we can do that with multiple threads, and we don't have any problems with threads needing to access the same data at the same time. So there's no locking or anything involved there. So we can do very effective parallelism on processing the root set. Now, the application is running at the same time. So at some point, we may get a situation where the application needs to access an object. And in order to make sure that that's perfectly safe, we do our test and jump. So we use the loaded value barrier. And so effectively, in the application thread context, what's happening is we're doing a very small amount of garbage collection work. The application thread will do a test and jump, and it will say, in this case, the bit is not set to indicate that's a live object. So we'll jump to the handler, we'll set the bit, and then we'll allow the object to be used by the application threads. So it's guaranteed to be marked. However, obviously that might then have other object references that we need to trace, but we don't want to do that work in the context of the application thread because it could take a long time. What we'll do then is we'll simply hand that to the garbage collector and let it do the work, and so it can then trace the other things as part of the root set. Relocation phase is about moving objects around within the heap or copying them around within the heap to eliminate fragmentation and to compact them. So if we look at the heap that we've got here, and we've got 5 objects, A, B, C, D, E, and we need to relocate them to make them contiguous. So that's very easy. We take some free space and we just move A to A prime, B to B prime, and so on. So that's effectively compaction. In order to do that safely, we will put a lock around the copy of that object, and we will guarantee that if you're trying to access an object, it will be locked while we're doing the copy, but because the objects are likely to be very small, the time it takes to copy that object is going to be very small, so any pause effect you will see will be almost negligible. The other thing we do is we build a side table, and the side table records all the changes in reference so that we know that A goes to A prime and B goes to B prime and so on. The other thing we can do, and this comes back to the idea of our Zing system tools, is enable better mapping of the way that the physical and virtual address space works. Effectively, this allows us to fully garbage collect any amount of memory with only 1 page free per thread that we use in the garbage collector. The way that we do that is we use our free page, and so obviously you can see here that the free page is the red one. We've used that to map the first couple of objects or copy the first couple of objects. But then in order to copy more objects, we need another free page. Now, because we know we've written the garbage collector that the first 2 there, A and B, will never ever be referenced again, we can actually steal the page from underneath in terms of the physical mapping and reuse that and copy new objects in the virtual space using that physical page. And then again, we can use the next page there that we've freed up and use that for the next copy. So that's what we call quick release, and allows us to again, optimize the way that we use memory in a much better way. Having done the relocation, we then need to do the remapping, which is where we need to update all the object headers to say that we're pointing at the right place. So in this case, again, what we're going to do is we're going to have a number of threads that will work through the list, and they'll use the side table, look at the reference changes and say, okay, A needs to be remapped to A prime. So the garbage collection thread will then update the object header in for that object and set the bit to say this has been updated. And then obviously we can do multiple threads, we can do that in parallel. Our application is still running. So at some point we may get an application that needs to access an object which we haven't remapped yet. Again, we use our test and jump. We look at the bit, say that hasn't been set, so we need to jump to our handler. The handler will do the same effective job as the garbage collection thread. It will take the remapping, update the object reference, set the bit, and then return it to the application. So the application is guaranteed that it will get the right place for the object in order to make changes. Now, the important thing about that is it means we can do very big heaps without any issues. So we can scale all the way up to 20 terabytes of heap, and you will see no degradation in pause times as you scale all the way up to that size. This is very good because a lot of people we see, to minimize pause times, will divide up a big set of data into multiple smaller JVMs. And that makes life a lot harder because you're trying to then coordinate work between different JVMs. And so having one big JVM, one big heap, makes life a lot easier. One important thing to say is Zing, although it works very well with big heaps, doesn't require big heaps. You can work with small heaps if you want, all the way down to 0.5 GB of heap is the minimum that we support. Okay, let's quickly talk a little bit about GC tuning, because this is something that we see a lot of people spending an enormous amount of time and effort trying to do. And they try to eliminate the problems of garbage collection by tuning away the pause times and doing all sorts of things. Now, the reason this takes so much time and effort is because there are so many ways that you can change the way the garbage collector works. There's literally dozens, if not hundreds, of command line flags you can set to change the way the garbage collector works. And if we look at this particular slide, this is two real-world examples. I'm sure people know about these things and they've seen this before. This is two real-world examples of people who've set up parameters for their garbage collection. And I won't go through all of this, but just highlight one particular thing, which is both of these customers set the survivor ratio. One set it to 128, one set it to 2. And the question is, what's the right value? And how do you know what the right value is? Is it 128? Is it 2? Is it 64? Is it 17? Probably not 17 because that's not an even number. But the point is, it's a problem because you end up doing trial and error. So you try, okay, 128, that gives you some performance. Try 2, that gives you worse performance. So try 64 and so on. And the real issue is that that's not the only parameter you can change. You end up with an n-dimensional space of different parameters that can be changed, and trying to find the optimum level, very, very difficult. How does a set of parameters look if we're tuning Zing? Well, it's a lot simpler. That's it. Just set the heap space and let the algorithm do its work. So realistically, from a performance tuning point of view with Zing, all we do to start off with, we do have a couple of flags that we can change as well, but they're literally about 4 or 5. So we say, okay, set the heap space, get the application running the way you want it to, and then reduce the heap space until you start seeing a fall off in performance, and then turn it back up a bit so you've got some headroom for your application, and that's really all there is to it. Okay, how can I show you that this actually works? Well, what we've done is we created this little open source tool called JHiccup. And JHiccup is designed to monitor or measure the latency associated with the JVM and everything below it. So it doesn't look at latency for your application code, it's latency of how the JVM is working with your application. To do that, we put a thread alongside your application code, but it doesn't have to interact with it. So there's no changes to your code. And also to avoid the problems of Heisenberg's uncertainty principle, the act of observing something changes what you're observing, we spend most of the time with that thread asleep. So the thread starts up and goes to sleep for 1 millisecond. When it wakes up, it looks at the system clock and says, I expected to wake up 1 millisecond later. What's the actual time when I woke up? If a 20 millisecond garbage collection pause kicks in, then we'll wake up 20 milliseconds later. We can record that change, and then we can produce some histogram files, and then we can create some nice graphs. And this is the kind of graph we can produce. So this is a big heap, big-ish heap. It's 128 gigabytes. So this is running Elasticsearch. And what we did was we ran with Hotspot, and then using the exact same machine, exact same setup, everything. All we did was change Java Home, point it at Zing, run the same tests, and get a different set of results. We look at the graph on the left. This is basically showing us latency. So high is bad. And what we're seeing there is a very typical graph for hotspot. So you're seeing lots of small spikes. That's your minor GC pauses. We're seeing two big spikes, which are the major GC pauses. And that's a very typical kind of graph. Lots of small spikes for minor GCs, occasional spike for major GC. If you look at Zing on the right, again, same application, same setup and everything, and you might look at that and go, "Ooh, that doesn't look so good." There's lots of big spikes on that graph, and it's very random. So how are you saying that's better than what we've got on the left? And the answer is I've been very deceptive here, and I've deliberately done this because I've scaled the graphs differently. So if you look at the left-hand side, it's scaled from 0 to 8 seconds, meaning most of those minor GC pauses are half a second. The two major GC pauses are around 5.5, 6.5 seconds. On the right, I've scaled it 0 to 80 milliseconds. So those spikes are considerably smaller than the ones on the left. If I scale the graphs to be the same size, then you actually get to see the effect of Zing. It literally eliminates all of those garbage collection pauses. It just flatlines, and you have to change the scale in order to see the effect of Zing on that. Many of those spikes you see on the graph before are actually due to effects down at the operating system level and the hardware level because they're that small. Similar thing, small heap. So we still get the same effect with the small heap. This is a Hazelcast node running on a 1 GB heap. Again, this time I've scaled the graphs the same, but you can see that with the hotspot side, we're seeing a lot of very heavy garbage collection activity. I would say they probably haven't set up the right heap size there. But even with that, if we use Zing, you can see again, it flatlines down, eliminates all of those spikes, and the whole problem goes away. Okay, so that's garbage collection. Now what can we do in terms of JIT compilation? So we talked about the fact that we have this approach where we take interpreted mode, then we go through C1 and then C2, get to our optimum level of performance. And what we did is we looked at that and we said, well, okay, can't really change interpreting, not really much to be gained by changing C1. The biggest benefit is going to be by changing C2, and that's what we've done. We replaced C2 with what we call Falcon, and Falcon is based on another open source project called LLVM. It's been around for quite a while now. It's designed primarily to produce the back end of compilers, static compilers, C, C++. And what we did is we said, okay, that looks really good. It generates very heavily optimized code. Let's use that, integrate it into the JVM, use it as a JIT rather than static compiler, generate the code from the same intermediate representation, and optimize our code for applications in a better way. And that's what we've done. So we've contributed those changes back to the project. What it enables us to do is get better performance. So we can use better intrinsics, we can do more inlining of code, all sorts of things like that that give us better results. Just to sort of give you an example of that, this is a very simple piece of code. So we're taking an array of ints, and then we're just adding them up. Now, if you give that to any modern compiler, it'll look at that and say, okay, we can use vector operations on that. And a vector operation uses very wide register, 256 bits, 512 bits, and loads up multiple elements into that register and applies a single operation on all of them in one clock cycle. So it's single instruction, multiple data. Been around for a while. So that's all good. Modern compiler will optimize that. However, if you give it something a little bit more complicated, you'll see that in this case, we've got a conditional. We're saying, okay, let's add 2 arrays, but only if the second element is even. Give that to a modern compiler, and a lot of them won't be able to recognize that as being something that you can apply vector operations to. In the case of Falcon, it does. So if we look at the bytecode, or the actual, sorry, not bytecodes, but if we look at the instructions that are generated by the compiler, we'll see something like this. So this is just using hotspot and C2. Don't worry about all the details of this, but essentially the red boxes here indicate that the optimization that's being applied is very simplistic. It's only doing what's called loop unrolling, and it's being able to do 2 elements per iteration of that loop to try and improve the efficiency of it. If we look at the same piece of code compiled with Falcon and using a fairly modern processor, it's a Broadwell E5, we'll see that very different looking code. Now, it looks more complicated, but what's actually happening here is we are using the AVX, in this case, AVX2 instructions, and that enables us to do multiple instructions on with a single instruction, multiple data. So the effect here is that we're able to load up multiple elements of the array, and we're also, in this case, doing 4 elements per iteration. So loop unrolling 4 times rather than 2 times, which gives us 32 elements being processed per iteration. And because many of them are being done in parallel, the effect on, in this case, numerically intensive operations is going to be very profound. And so we'll see a big improvement in performance. That's just one aspect of what we can do with Falcon. There's lots of other things we can do as well. And because it's a more modular design, we're now able to apply all sorts of interesting things. And that's what we're really working on. So last thing to talk about is ReadyNow and eliminating this warm-up problem. So we saw that we go through this phase of having to like compile code with C1, profile it, then we compile it with C2 or Falcon. And the problem is that we have to do that every time we start up the application. So we're doing the same warm-up thing every time we start the application. With ReadyNow, what we do is we say, okay, let the application warm up, get to a point where it's a steady state and you've got a happy warmed up application. And then we take a profile. And that profile consists of 4 pieces of information. Consists of all the classes that are currently loaded, consists of all the classes which are currently initialized in the JVM. Then we record all the profiling data that was collected during that C1 compiled code before it was passed to Falcon. And then, very importantly, we record all the speculative optimizations that failed so that we don't make the same mistake again. So we've got a situation where, okay, we tried a speculative optimization based on the way that the profiling data worked, and that didn't work out. So record that so we can avoid that. We can record that data over a much longer time. You don't have to wait just a couple of minutes. You could wait a day. You could wait a couple of weeks if you want to. It's really down to you as to when you're happy with the performance level of the application. What we then do is when you start the application, before you get to your main entry point, your public static void main, we will actually load all the classes that we can load from that list, initialize all the classes we can initialize, and then we will compile, if necessary, all of the code that's required for the methods that were compiled in the previous run of the application. All of that happens before we get to main. And the effect of that is that when you enter main using ReadyNow, you're at about 98% of the performance that you had when the profile was taken. What we typically find is you need about 2 or 3 transactions to be processed to get you to that 100% level, but 98% of the performance that you get already. And then the last thing we've done more recently is called compile stashing, where rather than having to compile everything in advance each time you start up the application, we also record all of the compiled code. So if that matches against the profiling data in the method, we can reuse that and eliminate a lot of the time that's required to do the compilation. So it starts up even quicker. Effect of ReadyNow is very similar in terms of looking at the graph. So this is latency. What we can see is that without ReadyNow, we go through the warm-up phase, optimization, deoptimisation, and so on. With ReadyNow, we get a nice flatline graph, no latency associated with that. So it's much better in terms of performance. Just to summarize, essentially what we say with Zing is the JVM that's designed to start fast, is designed to go faster, and it's designed to stay fast. Addressing all of those key points. So eliminate as much as possible the warm-up phase, eliminate the garbage collection pauses, and actually raise that level of optimum performance beyond what we saw in the 100% to give better performance overall for applications. Key thing is it is a drop-in replacement, so there's no requirement to change any of your code. There's no requirement to recompile it or anything like that. And if you're interested in this, we do a free 30-day trial. You can go to azul.com/Zing trial, and you can look through that and see, and you can try it out. We'll even give you some help creating those nice graphs so you can show them to your boss and say, look, this is how we can eliminate latency in our applications. This is what we need. And so that's the end of the presentation. So that's pretty much 40 minutes on the dot. So what I'll do now is I will see whether we have questions. So let me see. I'm going to stop sharing my screen. And then let's go to the.
So yeah, Simon, thank you very much for your great talk and great insights about the possibilities you have with that new approach to garbage collection. Very interesting. We're looking at the chat. We now have some time for questions. I can't see any questions so far here in the chat. So feel free to post anything. Also, of course, comments or a big applause. That's also a virtual applause to you here in these times. Very helpful. I can ask, what are your plans? Is there something coming up or some new features, some plans regarding Zing?
Yes, I mean, we're continuing to work on this. And the real idea behind the is most of our improvements at the moment are looking at how to get better performance out of the Falcon JIT compiler. As I said, it's a modular design. And so having done the sort of hard work of integrating it with the JVM itself and making it work with things like the garbage collector, what we're now doing is focusing on things like escape analysis and some of the other things that we can do in terms of better intrinsics to optimize that code even further. And literally any time that we find where there's a benchmark where we don't get as good a performance as we expect, then we treat that as a bug. And so we start looking at how to improve that and get better performance from that. I did see a question actually there. Let me have a quick look.
There is a Richard asking, is Zing for every application better than, for example, Oracle?
And I'm going to be honest about that, and I'm going to say no. There are a lot of situations where you get better performance, but there will certainly be situations where we see that the hotspot does actually perform slightly better than Zing. So depending on what the application is, there's a very wide range of places where it does work better, but there are a few situations we've seen where we've spoken to customers, they've tried it out and they've gone, actually, you know what, we get better results with hotspot. So I'll be completely honest about that. And profiles of applications are very variable. And so you may well find there is a situation where you get better performance with hotspot, but there's an awful lot of situations where, especially with the whole idea of eliminating garbage collection pauses, that can be very beneficial in that sense. So I'm seeing another question here. Any crashing known issues different from the JVM? Our JVM never crashes. That's probably a bit of a wishful thinking, but no, I mean, the great thing about Zing is it is a very stable platform. We started development of Zing back in, I think, 2008, maybe even 2007. So this is a 13-year-old JVM, certainly in terms of the work we've done on it. We've been working on it a long time. We have some very smart people working on it. So we've ironed out a lot of the early problems that we had in terms of developing it. So we do have a very, very solid platform here in terms of making sure that there won't be any crashes associated with the JVM.
Yeah, a lot of people are wanting your slides.
Yes.
That I can answer them. Of course, yeah, you can have the slide deck. After the conference, we'll get an email with the access to the slides of the talk. On the one hand, on the other hand, also this video recording, the session is recorded. Here is available for 1 year in Swapcard. So if you want to see it again, you can go back and forth and yeah, go into the detail of your flags. Or
right. Yes.
One of the options you have. Yeah, I think that's it in the chat. So yeah, thank you very much again, Simon, for this great talk.
Thank you. We
continue here in 1 hour. Now we have a lunch break. We continue in 1 hour with our next talks. And yeah, thank you for being here.